Okay, so I guess let's get started. It's our pleasure to have Austin here to talk to us today. Austin is an undergraduate from Texas A&M who went on to do his PhD at MIT under Günter Rowland, working on the CMS, looking into atomic energy loss via charged particles. I graduated in 2019, I think it was, and is now a Rice postdoctoral fellow at Rice University, working still on CMS, but he's now moved his islands and more into looking into jets and their substructure. And I think that's what he's going to talk to us about today. So it's great to have him here. Looking forward to your talk.
Okay, well, thank you very much for inviting me. It's a pleasure to be here and be in New Haven. So as Helen said, I'm going to be talking about jets and trillion-degree matter, and in particular, how we can use them to study QCD and multiple scales. So I'm going to start with the standard model. So the standard model is our theory that describes three of the four fundamental forces of nature. It essentially describes how these particles shown here all interact with each other in order to create most of the phenomena that we observe in everyday life. And you can actually write this down in some type of kind of compact notation here that fits on the side of a mug, but in fact, there's very, very complex dynamics involved in this. So the force in the standard model that most people are familiar with is electromagnetism. Our theory for that is known as quantum electrodynamics, or QED, and that describes the interactions of particles that have electric charge, for example, the one shown here, and with electric charge actually interact via the exchange of a gauge boson known as the photon. That is kind of described by this diagram here, where you see the electron, in this case, emitting a photon. So this is kind of how we describe QED. But we actually have also a theory for the strong interaction. And the theory for this is known as quantum chromodynamics. So it's called quantum chromodynamics because it describes the interactions of particles that have so-called color charge, which are shown here, the 6 quarks and also the gluon, which is the force carrier. And QCD is interesting because not only does it have this vertex similar to QED, but also the gluons are able to interact with themselves. And in fact, this gluon interaction leads to very non-trivial behavior of QCD and makes it very interesting to study. One of these interesting behaviors is known as asymptotic freedom. So what's shown on this plot on the right-hand side is on the y-axis, this is essentially the strength of the strong interaction. And on the x-axis is the momentum that is transferred in the interaction. And so you can see that if you go to large momentum transfers here, the strength of the interaction is fairly small. And so because of this, quarks in this kind of large momentum region don't interact very strongly, and they're relatively free. This is known as asymptotic freedom. And because this interaction strength is fairly low, we can actually use perturbation theory to do calculations. This is known as PQCD, or perturbative. If you go to low momentum transfers, this interaction strength increases very, very quickly. And in fact, at a certain point up here, perturbation theory no longer works because your series do not converge. This is known as the non-perturbative region. And in the non-perturbative region, it's very difficult to do calculations. So we need experimental input there. And also, this non-perturbative region leads to very interesting dynamics that we can study experimentally. One of the results of this non-perturbative region is so-called color confinement. So if you think of two quarks that are interacting with each other, you can actually show, for example, in this plot here, the field lines, the color field lines between the two quarks. And they tend to actually form this type of kind of tube between them. So this is known as a color flux tube. And if you increase the distance between the quarks, actually what happens is that this tube more or less elongates. And so if you plot over here on the right-hand side, you can see there's actually kind of a linear rise as you separate these quarks apart from each other. So that's very interesting because what that means is that as the quarks get separated towards infinity, you don't have some energy potential that converges to zero, like a 1/r potential in QED. And in fact, the energy of your system will actually increase to infinity, which is non-physical, you can't have infinite energy. So what actually happens here is if you take these quarks, you separate them, at a certain point, it becomes energetically favorable to actually make more quarks out of the vacuum. And that allows these color field lines to be terminated, and we basically get two pairs instead of just one pair. And so what this results in is that all these quarks are essentially combined into little packages of quarks and gluons that we call hadrons. So hadrons are like protons and neutrons. Those are, the everyday particles that make up the nuclei inside of us, but it also includes things like ions, kaons. So hadrons, although actually, because of non-perturbative dynamics, are a little bit more complex than just a bag of quarks. They actually also have a very interesting structure themselves. So for example, here you can see, for example, a proton, a schematic of a proton where you have kind of like 3 quarks inside of it. But if you increase the energy at which you probe the proton, you actually can see, because the non-perturbative effects, you actually get more and more gluons within the proton. And so the energy at which you probe the inside of a hadron actually causes what it looks like inside of the hadron to change. And so we can actually study this by actually kind of picking a given momentum that we want to probe a hadron, and pick a given fraction of the quark-gluon inside the hadron we want to probe, and we can basically make a measurement at some point in this plot. And then we actually have theories that allow us to extrapolate in different directions in this momentum transfer and parton fraction space to essentially learn more about how the hadron structure depends on the energy you probe it at, and also the momentum of the quarks and gluons inside of it. So that's one way we can study how QCD works. There's also another way of studying how QCD works, and this is by looking at the phase diagram of matter made out of quarks and gluons, or known as QCD matter. So for the nuclei inside of us, right, we are at a relatively low temperature. So if I plot this on a plot here where I have temperature on the y-axis, we're somewhere near the bottom over here, and we're at 900 MeV of this value known as the baryon chemical potential. If you're not familiar with the baryon chemical potential is, you can kind of think of it as the number of quarks in your system minus the number of antiquarks in your system. So the excess of quarks is similar to that. So we live kind of here in this phase diagram of quark and gluon matter. Over here is what you get whenever you have some dense matter, such as cold dense matter, like a neutron star, for example. But what's interesting is that if you take this matter and you heat it up, so if we go this way in our diagram, there have actually been calculations done on big supercomputers known as lattice QCD that show that as you increase the temperature, the number of degrees of freedom of the matter actually increases in a transition around this temperature, critical temperature. And that is actually a transition from this phase of matter into a new phase of matter with larger number of degrees of freedom. And so this is essentially what you can think of this as, is taking your hadrons and melting them as you increase their temperature. So the quarks and gluons inside of it kind of get removed from that bag of quarks and gluons and are free to move around. And this phase of matter is known as a quark-gluon plasma, where you have deconfined quarks and gluons that can move. Now, the quark-gluon plasma is very interesting because of many reasons, but one of the reasons is because in the early universe was very, very hot. And so it's actually predicted that most of the universe consisted of a quark-gluon plasma at very early times, just after the Big Bang. And so by studying this quark-gluon plasma, we can actually study essentially the dynamics of the early universe. So in order to make a quark-gluon plasma, what we do is we actually take an atom smasher and we collide ions together. It's shown by this cartoon. Here, the ions are shown as pancakes because they're moving at nearly the speed of light. So they're Lorentz contracted. They're not spheres, they're pancakes. And we collide them together. That actually heats them up enough to make a quark-gluon plasma. And this quark-gluon plasma has been measured to be roughly 5 trillion Kelvin, which, to give you a sense of scale, is something like 100,000 times the temperature of the center of the sun. So this is incredibly hot matter. After we create it, it cools down. And as it goes through this transition, it then becomes hadrons once again because they're confined. And we can actually detect those hadrons in our particle detector. and we can use that information to infer about what happened in the quark-gluon plasma. And so this is how we learn about the quark-gluon plasma. And in fact, we've learned that the quark-gluon plasma exhibits very complex and interesting phenomena that are actually fairly difficult to describe by individual interactions between just simple atoms. So I said we use an atom smasher to collide these collisions. So there's two facilities I want to talk about that do this in my talk. First is the relativistic heavy ion collider shown here. This is at Brookhaven National Lab, just south of here on Long Island. RIC has a top energy of around 200 GeV per nucleon pair, and it's very flexible in that it can accelerate almost any element. So you can accelerate protons all the way up to like uranium. There's another accelerator, which is the one that I have worked on for most of my career, which is the Large Hadron Collider. This one is based in Geneva, Switzerland. So this one only runs about 1 month out of the year because it also shares time with the high energy physics proton-proton community. So we run for less time. However, it does have a higher energy of around 5.5 TeV per nucleon pair, which if you multiply by the number of nucleons in the nucleus is something like 1 PeV of total collision energy. To give you an idea, a sense of scale, this corresponds to in SI units about 0.1 millijoules. So you can actually use joules, which is kind of a more macroscopic quantity to describe the energy of literally two particles colliding. So it's a huge, huge amount. So LHC is more limited in the amount of ions that it can collide. So it can do protons, lead, and xenon for now. So now what I'm going to show you is I'm going to show you a simulation of what these collisions look like at the LHC. So these lines here, you can think of as the beam pipes that carry the protons coming in, and you'll see there'll be a collision. From the collision are hadrons that come out, and they go in circular trajectories because there's a magnetic field, and because they have charge, they actually bend. Okay, and the time scale of this simulation is roughly 1 billion, a downscale of about 1 billion. So 1 second in the simulation is actually 1 nanosecond. Or sorry, 1 second. 1 second in real life is actually 1 nanosecond. So these are proton-proton collisions. But sometimes you have proton-proton collisions that have a little bit more interesting dynamics to them. For example, if there's a very hard momentum transfer, you can get a spray of particles all going in one direction like this. This is known as a jet. I'll talk about jets a lot more in this talk. And so this is what happens when you have a very large momentum transfer in a proton-proton collision. Here's another example. And now I'm going to show you a heavy ion collision, which looks very different than proton-proton collisions. Coming up in just a second. This is a heavy ion collision. As you can see, there's many, many more particles produced. And in fact, the lifetime of the quark-gluon plasma produced in this collision is 1 trillionth of 1 frame of this simulation. So what we're seeing here is actually the hadrons coming out of the quark-gluon plasma. We have to detect those hadrons to actually make inferences about the quark-gluon plasma itself. And so in order to detect all those hadrons and calculate their trajectories, we need a particle detector. So this is the particle detector that I work on. It's known as compact neutron solenoid, or CMS. It's a general purpose experiment. It's about 50 feet tall. So to give you a sense of scale, there's a person right there. There's another person down there. So it's very large. It weighs about 14,000 tons. So don't be fooled by the name compact. This is actually a very, very large experiment. It has around a 4 Tesla magnetic field inside of it. That's about the same magnetic field as an MRI machine. But you know, most MRI machines are about the size of a human, not the size of a small house. And it has around 2,000 collaborators like myself who work to make sure everything operates correctly. Here's an example of a lead-lead collision in CMS. This is data. And as you can see from this big blob of particles, it's very challenging to follow the individual trajectories of every single line in these high occupancy events. But that's actually something that I worked on for a long time, leading a group doing that in CMS. And also, because there's so much information, this is actually very stressful for the data acquisition systems and the detector. And so I've recently been leading a group to try to optimize the data acquisition of this in order to make sure we can get all this information out of the detector. And I'll talk a little bit more about that later. Okay, so we have a detector and I said we want to make inferences about the quark-gluon plasma. So what are some of the things that we've learned about the quark-gluon plasma? So one of the first things that was discovered at RIC was that if you look at the correlations between particles and you plot them in this kinematic space where the difference in the azimuthal angle and the difference in their pseudo-rapidity, we found that there was actually a bump here that's known as the so-called near-side ridge, which is a hallmark of what is known as collective motion and flow. And based on these observations, people have actually been able to extract the viscosity of the quark-gluon plasma. So that's what's plotted here is a ratio of viscosity over entropy density as a function of temperature. You can see water is up here in the plot. Superfluid helium is less viscous. And then you have the quark-gluon plasma here, which is even lower. This is a very non-viscous material. And in fact, there's actually theoretical limits shown here done by these fancy calculations. And you can see the quark-gluon plasma is near this limits. That's why they call it a nearly perfect fluid. And this is very interesting because, you know, I told you that we're essentially melting hadrons and freeing the quarks and gluons inside of them. A lot of people at the time thought perhaps they would behave more like a gas, right? Weakly interacting. But because it's a non-viscous fluid, that actually means that there's very strong interactions within this medium, even though it's deconfined. And so because of that, it's very interesting to study the microscopic dynamics of these very strong interactions of this medium. So in order to study the medium at a very short length scale, where you're looking at the microscopic interactions, you need a probe that has a very short wavelength. So I told you, ideally we'd like to do this by like shooting a color charged particle into the quark-gluon plasma, like a quark or a gluon. But we can't just have an accelerator shoot one quark because, as I told you, color confinement means you can't have an individual free quark. So what we do actually is when the ions collide, sometimes there's a hard scattering that produces a jet, which is one of those sprays of particles I showed you earlier in the presentation. And so what happens here kind of at the Feynman level, Feynman diagram level, is you have some hard process shown by these tree level diagrams at some hard scale where you can use PQCP. And then as this quark or gluon, which is known as a proton, propagates, it actually radiates additional radiation because it can't be free by itself. And it leads to the shower, the so-called proton shower. As this shower progresses, this scale gets lower and lower until eventually you reach a scale here where you're kind of in the non-perturbative region. And then you undergo what's known as hadronization, where these quarks and gluons turn into hadrons, shown here. You detect these hadrons in your detector as a spray of particles that I showed you earlier. That's known as a jet. Okay, and the information of this jet, or the kinematics of this jet, actually give you information about this entire process, and in particular about the kinematics of this initial hard scattered. Okay, so I think my laser pointer has died. I will just. So we can learn about this initial hard scattered proton and use it as a short wavelength probe of the medium. So in particular, as I said, it's a short length probe. What we can do is we can experimentally compare, for example, collisions where there's a quark-gluon plasma and collisions where there's not a quark-gluon plasma, and we can actually compare the proton showers. And you can see that in the quark-gluon plasma, it's predicted that there's additional radiation and collisions that are induced by the presence of the medium. And so what this means is that if you have, for example, two jets, which should be balanced in momentum, if one jet exits the quark-gluon plasma, which is shown by this kind of dark blue circle here, and the other goes through the quark-gluon plasma, this one will lose additional radiation into the quark-gluon plasma through induced radiation. And what that shows up as, if you plot this kind of in your detector, shown over here, then you see unbalanced jets where they should be balanced, but one has clearly lost a lot of energy. So this process is known as jet quenching. And this is a direct result of the interaction of your hot medium interacting with your jet, which is a PQCP code. And so this is a very interesting effect to study. And we've actually learned that not only do the jets themselves completely lose energy, but actually particles inside the jets also on average have less energy. So as part of my thesis, I actually studied the effect of the individual particles inside the jet. And so I did this measurement here. The new measurement is shown by the points with the yellow boxes around them. And you can see that in this observable, what we do is we compare lead-lead collisions to proton-proton collisions with an appropriate scaling factor. We take a ratio. And in that observable, essentially, if there's no quenching, then you would expect this value to be at 1. We clearly do not see that based on the data. You can see there's a huge suppression, and that is a direct result of jet quenching. So this is a quantification, thank you, of jet quenching. And you can see here on the right-hand side that this paper in particular is very influential, has over 280 citations, but also it was picked up by the CERN Courier in celebration of the 30th anniversary of heavy ion collisions at the LHC. And that's because this observable has been measured many, many times, and it's kind of a hallmark measurement of the heavy ion community. They're both great at the LHC. So I actually did another measurement of a very similar observable, but doing it in xenon-xenon collisions. In xenon-xenon collisions, the ion's a little bit smaller. So you expect, since you go through a little bit less quark-gluon plasma from the smaller ion, you get less quenching. That's indeed what we saw. But what I want to point out, though, is that on this side here is that when we compare the models, you can see all the models are able to predict the data, mostly because a lot of them were tuned with very similar previous data. However, what that means is that this observable doesn't have a large amount of distinguishing power between models, right? So we need other tools in our toolbox in order to learn more about how to distinguish various models. So another tool we have in heavy ion collisions is to use probes that have no color charge. So for example, in the standard model, the photon and the Z boson don't have any color charge. So they're expected to more like pass through the quark-gluon plasma without interacting with it very strongly. Also for the electron and the muon, which are the decay products of the Z boson, this is a similar story. So you can see, for example, in this event display, you have a jet produced one way and the Z boson that decays to 2 electrons the other way. They should be balanced in transverse momentum, but the Z boson will not be quenched, whereas this jet may be. And so we can actually use this kind of as a control measurement to compare jet quenching. So that was kind of the motivation for this analysis. What we did was we looked at Z bosons, which were the unquenched particles that I mentioned. That's shown by the black data points here. And then the hadrons from the previous 2 slides that were very suppressed are shown here. So this is plotted as a function of basically your impact parameter. So here you make a large amount of quark-gluon plasma. Here you make a small amount, or maybe no quark-gluon. And so you can see that for Z bosons, there's not much suppression, whereas for hadrons, there's a very large amount. So this is a very nice kind of confirmation that this effect seems to be coming from the presence of color charge on the quarks and gluons, so quenching. And also, actually, what we saw is that in these kind of collisions where you don't make very much quark-gluon plasma, that there's actually a small dip here, which is very interesting. I don't have the time to discuss the exact reason for that, but there's a model that predicts some non-quenching effect, basically, that can explain why, for example, the hadrons, where you don't make a very large amount of quark-gluon plasma, still have some kind of residual suppression. So that was a very interesting thing we learned from using these bosons as a control for other measurements. You can also use these electrolytic bosons in another way. So here what we can do is we can study the balancing between the photon going this way and the jet going this way. And you can actually use this basically to learn about the energy loss of your particles within inside the jet. So for example, what we did here was we measured an observable known as the fragmentation function. So what's plotted here, if you just focus on the right-hand side plot, is this is a ratio of lead-lead to proton-proton collisions. High momentum particles will be shown kind of in the left-hand side of it, and low momentum particles will be shown on the right-hand side. You can see that in this measurement, basically, when you go to low momentum, you see additional particles being produced, and at high momentum, you have less particles produced. So this is consistent with the energy carried by hard particles being transferred to low momentum particles. So that's. We also did this similar measurement where instead of looking at kind of the transverse momentum, we looked at the radial profile of the jet. It's very similar measurement here, just changing the x-axis basically. This is known as a jet shape. And you can see here that as you go to larger radiuses, you see this rise. So not only does the energy go to lower, softer particles, but in general also goes to wider angles. So essentially this energy is being dumped into the plasma, so lower energy particles traveling at wider angles. So this is kind of consistent with many other measurements that have been done that have kind of learned very similar things. And then the question is, can we go even further, right? Can we use jets to learn even more about how the medium interacts? And so this is, I would say, a very new field of research, which is known as jet substructure. But in order to explain that, I first have to explain to you how we actually group particles together into a jet. I have to tell you the technical details because this is actually key to how we do these substructures. So in order to do this, what you have is, if you just imagine you have some particles shown here in one dimension, pseudo rapidity. In our detector, it's actually in 2 dimensions, but this is just simplification. What you do is you have an iterative procedure where you compare the distances between particles using this equation that depends on the transverse momentum and their angular separation, and you start grouping them together. There's a parameter here, p, that you can set to any particular value. Common ones are p equals -1. These are known as anti-KT jets, and they tend to be circular. And you can also use p equals 0. This is known as the Cambridge-Hawkins algorithm. So in this example, I'm going to use Cambridge-Hawkins algorithm because it will just simplify this equation a little bit. So if you use p equals 0, then it becomes this, which is just the distance and angle between the particles, right? So you look at this, and you look at the pair that has the smallest distance, which is this one, and you group them together. And then you repeat your iterative procedure. So the next closest pair is this one, so we group them together. Then it'll be this one, so we group them together. You repeat this procedure, and you build up this type of tree, right? And finally, you end up here with all of them grouped together. That is the direction of your jet. And the energy of all these kind of averaged together is the energy of the jet. So that's kind of the algorithm we use. Now, the reason why this tree is important is because this actually includes a lot of information that's very similar to the parton shower that I showed you earlier, right? So the branchings here actually are correlated with what happened here. And so what we can do is we can unwind this branching to actually go back in the evolution of the shower to access the early time branchings. And as I said earlier, this is a very hard scale at the beginning of the shower. So this is where you can actually use perturbative QCD to make predictions. So we can actually kind of unwind this tree to look at kind of the PQCD part of the shower. So in order to do this, we use kind of a backwards method. What we do is we look at the thing. Basically used to, right? We check if they meet some condition known as a stop drop condition, which depends on their angle and their momentum. If you fail that condition, which in this case it would, you actually drop the lowest momentum branch, which would be this one, and you go to the next one. So we drop this branch and we look over here, right? And then we have this tree and this tree. This actually passes, so then you just stop the procedure. And when you stop the procedure, you end up with 2 kind of separate branches. These kind of correspond, for example, to this parton outgoing and this parton outgoing in your shower. And in your detector, these look as like 2 kind of smaller cones within your jet. These are known as subjects. And you can actually look at the kinematics of these subjects to learn about what happened here. So this is the idea of this so-called jet grooming and construction. So there've actually been some measurements done of this in heavy ion collisions. This is the measurement we did in CMS. So what's shown here is lead-lead splitting function divided by proton-proton as a function of this variable ZG. ZG is essentially the minimum of these 2 momenta divided by their sum. So if these are evenly balanced in momentum, this is equal to 0.5. And if they're unbalanced, so this one has more momentum, for example, then you have a value that's lower than 0.5. So you can see from the data here, if you just focus on this top left block, you can see from the data that this is not 1, this actually rises, which means that when you put this in a medium, you actually favor more unbalanced splittings here. And in fact, this is predicted to be related, for example, to the dynamics of how the medium interacts with the jet at very early timescales, whether or not the 2 partons coming off emit coherently as kind of one effective particle, or whether or not they emit as two separate particles, because that changes your shower dynamics, which then changes the system. There have been another measurement done by the Alice collaboration here. So instead of doing the ZG, they look here at the RG, which is essentially the angular separation between the two jets. So if you look at the ratio here on the bottom, you can see that the smaller separation is slightly preferred by the data, but it's not a, let's say, huge enhancement. And you can also see that there's some model comparisons which, for the most part, can kind of capture the general trend, but they do have some spread here. So one of the things we noticed when studying these observables is that if we looked, for example, in proton-proton collisions, we actually saw that some of the models were unable to predict what we measured exactly, which was a bit surprising because I told you this is kind of a more PQCD-like observable, which means that even though we're doing these ratios with proton-proton collisions, it seems like we don't fully understand exactly what's going on in proton-proton collisions, even though we're using them as a vector. And so my colleagues were thinking about this, and we thought, is there a way we can kind of validate our understanding of proton-proton collisions with a simpler system? Because as physicists, we like to start from simple systems and kind of build our way up. And so in fact, we concluded there is a way. You can look at a system where you just have two individual quarks in the initial state going off in separate directions. It's a very simple system, just two quarks, and you can try to analyze what the dynamics of that would be. So in fact, there's a way to do this. You need to look at electron-positron collisions. The electron and the positron actually annihilate into a virtual photon or Z and make this pair of quarks, which is a very simple system. It's one of the simplest QCD systems you can make. The problem is that if you want to do this at a relatively high energy, nowadays you can't, because the max energy of electron-positron colliders is maybe 10 GeV or a little bit higher. However, in the past, this was done at 90 GeV at a collider called LEP. This was actually the LHC funnel before they put the LHC in it. So this was kind of done before the LHC. And so my colleagues and I actually got access to the data that was done here, gathered between 1990 and 2000, in order to try to make this measurement in this very simple QCD system to check our understanding. So here's an example of what electron-positron collisions look like. You'll see that compared to heavy ion collisions, they're much simpler. Many less particles. And you can see clearly you have one jet going that way and one jet going that way. That corresponds to the two quarks in the initial state, right? There's another collision, you can see one jet going that way, one jet going that way, right? So these are much more simplified compared to heavy ion collisions and even proton-proton collisions. So this is a nice way of validating our understanding of QCD at a very basic level. There's another one jet. So in order to do this, we need a detector. So this is the detector we use. The LEP detector has many of the hallmarks of modern detectors. For example, you have tracking, you have calorimetry. It looks very similar because it's a big circular cylindrical detector. So we did this measurement. So what's plotted here is, once again, the basically this so-called splitting function is a function of the ZG. And what you can see here is if you look at the ratios of data to models, the models actually tend to overproduce these unbalanced jets in electron-positron collisions. You can see it very clearly here in this jet energy, right? So even in electron-positron collisions, we don't, fully describe what is happening to the data. And in fact, here we see deviations that are in some of the models that are very similar to the deviations we saw in proton-proton collisions, right? We also did a similar measurement where we look at the angle. It was similar to the measurement I showed a few slides before. And here you also see that although we can kind of capture the dynamics in this kind of middling range, in the tails, you have a big spread of what the models are predicting, right? So really that kind of brings me to my next point, right? Which is, if we want to have a theory of QCD that can describe all of QCD systems, right, from electron-positron collisions where you have just two quarks, all the way to central AA collisions, right? We need to make sure that we have a solid understanding across this entire scale of system sizes, right? So what we can do is we can try to start at very simple sizes and build our understanding as we go, for example, to proton-proton collisions and then proton-A collisions, right? And in fact, I think there's a gap here between our understanding of electron-positron and proton-proton collisions, right? And there's more that we can do to see if we can build from here to here and enhance our understanding. And so there's some ways we can do this. In general, I want to talk about two methods. One, you can try to add some complexity to the simplest system you can think of, right? Going this way. Or you can try to remove some complexity from proton-proton collisions and go well. So I'm going to first talk about removing complexity. In proton-proton collisions, there was also another very interesting and perhaps surprising feature that was spotted at the LHC. So if you remember earlier, I said there was this little bump spotted in lead collisions at ring that was thought of to be a hallmark of it being a perfect fluid. We actually saw this bump as well in proton-proton collisions at high multiplicity. That was very surprising at the time because people thought you wouldn't have enough energy density to create a liquid, right? And so there's questions. What is this bump in proton-proton collision? Are we making really small quark-gluon plasma? Is it something else we don't understand that we need to try to understand? So people were asking this question, and it was proposed here to try to do the same measurement in electron-positron collisions because they're simple, right? In this kind of simulation, they said if you kind of tweak the interaction between the quarks, perhaps you could get a little bump here, right? Which would be simple. So my colleagues and I saw that, and we said, okay, let's try to measure that. So we did this with our E plus and minus data. We saw no bump, you can see here. And because we saw no bump, what we ended up doing was setting confidence limits, which are just shown by the red and black arrows here. Without getting into too much detail, because the plot's a little bit busy, essentially we just set limits as a function of the number of particles within your event. So we didn't see any bump anywhere, right? But when we were doing this analysis, this got us thinking, what we're doing is we are trying to learn about QCD by looking at a kind of heavy ion-esque observable in electron-positron collisions, which are essentially just two jets, right? So what we're doing is we're applying heavy ion observables to jets. That's fundamentally what we were doing, right? And we were thinking, in this study, we were limited by statistics because the data was taken 30 years ago. If we just want to apply heavy ion observables to jets, we can do that at the LHC, where we have a lot more data. The LHC is still running, right? We can produce a lot of jets. We can study them as a function of multiplicity. And in principle, we can do similar studies using proton-proton collisions if we just look at the jets inside. So that was kind of the motivation for this nice study that we did here. So this is a simulation study that we did with the graduate student at Rice, Parker. What we did was we took Pythia, which is a Monte Carlo generator, and we looked at high number of charged particles within the jet, right? And we tried to we explored what heavy ion observables we could look at in order to see if we saw something that we aren't expecting in these high multiplicity jets that might give us a clue about, for example, things like what the origin of that proton-proton bump was earlier, or maybe some other dynamic. So one of the things that we spotted was we can try to measure azimuthal anisotropies within the jets. The Monte Carlo generator doesn't expect these to be zero. They expect some non-zero values that are shown here. And the idea is to look in data and see if we match the generators or if there's, like, for example, some multiplicity dependence where something kind of goes up or goes down, for example, to see if there's anything else we can do. So unfortunately, I can't show you the data right now, but the first results from run 2 are coming very soon. So stay tuned for this. There's also another measurement I'm very excited about we identified in this same study, and that is searching for strangeness within individual jets of the LHC. So you can see here, this is the ratio of various identified particles to inclusive charge hadrons. They're mostly pions, but there's also protons, kaons, so on and so forth. And the idea is that if you look, for example, with jets with a large amount of particles, to see if we see something that deviates from Pythia, which is very flat, right? And in fact, a very similar measurement has been done already by the ELISE detector, shown in Nature here. And you can see here, this is the multiplicity of the whole proton event. So not just one jet, but the entire event. And they compared to Pythia, and you can see that Pythia here, once again, is flat, at least measures some very clear dependence, right? So we know if we look at the whole event, we see this rising trend, right, which is not described by generators. The question is, do we see that if we look at one jet? Because that tells us about the origin of this, right? If we don't see it in jets, that means that our understanding of hard QCD is fairly good, and this might be some kind of softer stuff. Whereas if we see it in jets, right, then that's something that we haven't predicted before. We should try first. So that's the idea. So I think this is a very exciting opportunity. So that's an example of how we can remove complexity. Basically, take proton-proton collisions, and we look at kind of an individual part with inside of them, just to get. Now I want to talk about how we can also build up complexity from simple systems, right? So starting from electron-positron collision. And the way we can do this is by taking one electron and colliding it with a hadron. We're actually going to be able to do this at the next big facility that's being built in the United States, known as the Electron-Ion Collider. As you can tell by the name, it collides electrons with ions, but it can also do protons as well. And this is kind of marketed as a machine that will unlock the secrets of the strongest force in nature. The way it does that is, if you remember this plot from earlier in the talk, we will be able to use the electron to basically pick out the point in this diagram. And then if we can, the idea, the Electron-Ion Collider is to try to push down to the low values in X to search for example, the saturation region, but also to study the dynamics of this kinematic space. So some of the questions that this promises to answer are things like doing detailed tomography of where the protons are inside the nuclei, so we'll understand the nuclei's structure much better. We can also answer questions, for example, about the nature of the proton spin. So there's a lot of questions about how the proton has a spin of 1/2 when the individual constituents inside of it have, spins of 1/2 or 1 as well, right? So how do they add together to somehow always make it 1/2? And then there's also a search for so-called phase of matter known as the color glass condensate, which is predicted to basically be some form of matter that is created in ions whenever you go to very low momentum fractions, based on how the gluons grow inside the nucleus at low energy. So this is kind of the way we're going to make the Electron-Ion Collider. They're going to take RIC, one of the types from RIC with the ions, and they're going to add on an electron ring and electron storage ring, so you can do collisions between the two. But they're predicting to have a very large energy range, high luminosity, polarization, so you can do polarized studies. And because it's starting from RIC, you can do many ion species, from protons all the way to uranium. There's planned to be at least one detector at the EIC, maybe 2, we'll see. But this one is the one that for sure will happen, is known as EPIC. So this is an asymmetric detector because the electrons and the hadrons come in from different sides and make a boosted system, but it will have like full tracking, particle identification, you'll have full ECAL coverage and very good HCAL coverage. So it's kind of got all the hallmarks of a nice general purpose detector. And then in particular, it has this so-called streaming readout is planned. I want to talk a little bit more about this streaming readout because this is something I'm particularly interested in, and it relates back to my work on CMS, getting all the information out of the CMS detector. So to explain why this is interesting, I'm going to first explain how CMS works, and then I'll show you how the streaming readout is kind of new. So on CMS, we take the data here at around 40 megahertz, and this goes directly into a whole bunch of electronic hardware, okay? And this hardware, what it does is it essentially forwards bits of the event into what's known as the L1 trigger, which is also a custom piece of hardware, electronics. That determines what events are interesting and not interesting. And based on that information, it will tell the subdetector which ones to forward for further analysis. So this hardware filter is a very, very stringent selection in the sense you go from 40 megahertz down to 10 to the minus 5 megahertz, right? Sorry, 10 to the minus 5 hertz. So a lot of events are already thrown out in your hardware, right? They don't even see a computer ever, right? Then you put the events that survive into a big computing center that has a lot of software. or sorry, a lot of CPUs. And then you can use software to do much more detailed analysis to really select the events that are of most interest. And those are the ones that you forward into your final kind of computing center. And there's a kind of interlink here that has 15 gigabytes per second bandwidth. So you have to make sure everything fits in those 15 gigabytes, right? Offline, then you can do things like you can group hits together into clusters. You can reconstruct jets, tracks, and you store them. So at CMS, I actually worked on trying to optimize the usage of these 15 gigabytes. And so what I did was I moved this clustering step from the storage center into the software farm here, right? So we do this actually a little bit earlier. And by doing this, what we do is we actually shrink the size of the data that we before we put it through this, we put it through that interlink. And that means you can put more events through that interlink, so you can actually take more data. And so this combined with the addition of GPUs in the software farm actually gives us a greater than 30% increase in the rate of heavy ion collisions taken by CMS for round 3. So this is something we tested in November and was quite successful. And in fact, we're now working with the proton-proton community in CMS to try to implement this for all CMS data, because they're also very excited about this to help deal with the high luminosities that they're facing. So this was a very successful program. And the EPIC streaming readout will have very similar characteristics. So what happens here is EPIC will have a very large amount of data coming from the front end of the detectors. And what they do here is they immediately put it into some firmware. And after a little bit of aggregation of the data, it immediately puts it into a huge computing center. So you remember I had that hardware filter that removed a lot of events. There is no hardware selection done in the streaming readout. Every event sees a computer, which can then do detailed analysis of whether or not we want to keep it or not. So you can be very selective on what types of events that you take using this system. So in order for this to work, you have to slim the data quickly in order to make sure that all the computers can handle it. So for example, what's done here is a clustering, which is very similar to what I was doing in CMS, where you move the clustering into the computers earlier to slim the data down. So I'm very interested in this because I think there's a lot of synergies with what I've done in CMS, for example. And I think this system is very interesting in terms of having opportunities, for example, for implementing heterogeneous computing, data compression algorithms, machine learning, AI. Now, okay, so we have this detector. What physics do we want to do with this detector, right? So I told you there was some kind of discovery potentials that I mentioned on the previous slide. But I'm going to talk about the physics that I'm particularly interested in now. So one of the things that you can do is if you have a parton kind of propagating through a nucleus. Now, mind you, we don't expect there to be a large quark-gluon plasma. So this kind of orange smudge is not really a quark-gluon plasma. It's what's known as cold nuclear matter, which is essentially just propagating through a nucleus before it has been melted. Okay. And you can actually study whether or not the hadrons are formed before they get outside of the cold nuclear matter, or if they form outside the cold nuclear matter. So you actually will have changes in your hadronization based on where this process happens. And you can measure that by looking at ratios of hadron production, for example. Also, you can use those methods I showed you earlier of subjet reconstruction to do studies, for example, of the amount of transverse momentum that individual protons get as they move through the cold nuclear matter. So that's what's shown here. This observable is the angle between subjets and the green jet, which is something you saw earlier. And you can see from models that if they give the proton different transverse kicks, shown by this value Q hat L, that you can actually distinguish that. So this is very interesting for constraining hadronization, cold nuclear matter effects. Also, we can use a similar observable, the CG of the groomed subjects, to look for things like the role of flavor and quark mass in the hadronization process. So remember, this ZG is this kind of balancing of the various jets. And you can see from this prediction that they predict a difference, for example, if you have a B quark or up quark in the ZG yields that you see here. So you can actually distinguish various effects from the quark masses. So let me come back to this. So I think we can add electron-proton, electron-ion collisions kind of here. And I think by building understanding of cold nuclear matter and of hadronization, that will help us bridge from these simple systems to the more complex systems, right? And so overall, we want to construct basically understanding of QCD that will apply in all of these collisions. So I think we should continue exploring, by all means, large-scale systems, right? There's a lot of interesting new things being proposed. They're very exciting, but also we can do work down here. So that brings me kind of to the future opportunities very quickly. So we have the LHC-13, which is starting now, which is very exciting. We can do very interesting measurements with jets and particle identification, high efficiency tracking that will occur for around 3 years. Then there's upcoming the Electron-Ion Collider, which will go through R&D and construction in the next decade or so, with some data around 2031, 2030. And then there's also opportunities for the LHC-14 here and 15 here. You'll have kind of upgrades to various detectors. And also there's a plan to do various ion species at the LHC, which has not been done before except for lead and xenon. It's been done at RIC, but it hasn't been done at LHC. And the idea here is that if you use the smaller ions, you actually get more nucleon luminosity, which means essentially more jets. So if we use these ions, we actually get more jets, which means we can do more jet physics. Okay, so that brings me to my summary. So jets are a very useful probe of QCD at both the hard and soft scales. And in fact, we can use them to probe this microscopic structure of the quark-gluon plasma to really understand what makes it, for example, a perfect liquid. And I also think that the EIC, while also enabling discoveries, will allow us to do really interesting precision QCD measurement. And for example, testing cold nuclear matter effects, hadronization, things like that. And hopefully we can build an understanding of QCD that spans all QCD systems, which I think it really is kind of the goal of all of this stuff. So that brings me to the end of my talk. Thank you very much.
So I guess now we're open for some questions. I'm going to open the floor to people on the outside. If anybody on the outside has a question, you have the floor now. If not, then we can open the room to people present here.
I have a quick question. It was around slide 20, I don't exactly remember, about the Z boson peripheral suppression. Can you explain a bit what HG50 has that's predicting that? Yeah.
Right. I have a slide in the background.
Okay. Sorry.
Yeah, so what this HG50 model is, okay, so there was this measurement done by the Alice collaboration where they showed charge hadrons kind of going up and then turning over as a function of symbology. And then there's this paper by this HG50 that showed they could actually kind of predict that trend. So actually, the reason we did this measurement was because this paper, we wanted to measure this HG50 line. What's inside of HG50 is essentially what they do is they overlay just proton-proton collisions on each other based on the encode, which is essentially the number of effective proton-proton collisions a heavy ion collision has. So there's no quenching model at all. They just overlay proton-proton collisions, and then they repeat an experimental procedure that is done similar to what we would do experimentally with the supernovae calibration. And so they found two effects that cause this suppression. So the first effect, which is shown, let's just focus on the LHC point, but it's also kind of generalized to the array, is the crosses here. And so this is related to the fact that if you have proton-proton collisions, these are protons, not heavy ions, right? If the impact parameter of the protons is smaller, there's a greater likelihood of having a hard process, at least in the models, right? And so what they found was if you think of a whole ion, right, as you separate the ions, you also are on average increasing the impact parameter of the individual nucleons within the ions, right? You can think of like a collision where the two ions barely touch, the two nucleons that barely touch will also have a very large impact parameter because they're barely hitting. So there's a correlation. This correlation effect means that the soft production, which is based on kind of the impact parameter, and the hard production, which is based on the impact parameter of the nucleons, not the whole ions, are correlated. This correlation did give us a little bit. Okay. So that's the crosses. Then there's a second effect, which is that experimentally, right, whenever we do the centrality calibration, we can't access the actual true value of the impact parameter. We're only doing kind of an averaging. So there's some fluctuations there. And that actually makes the second kind of point, which is the red lines here. So this is actually a combination of what I would consider physics, right? And something that is kind of an experimental technology. Right? Okay. But what's interesting, I think, is that in principle, this is something we can learn about at the EIC, right? Because this is related to the internal structure of protons. So that's something that's very interesting.
Sorry to make you jump back and forth. I have a question about the ZG. This might be an Elise bias question. Sure. I cannot help that. But so you mentioned like ZG, yeah, in relation to like being sensitive to color coherence effects.
Yeah.
I've never thought about it this way. I think that's because Elise doesn't measure a modification to ZG. If it were sensitive to color coherence effects, one thing I guess I'm confused by is why you would see like an increase in the shape difference at higher PTs. I would have thought that like as you move to lower PTs, if it is sensitive to color coherence effects, you would see an increase in this effect, which is mainly due to like changing quark and gluon fractions. So you're more likely to have like kind of jets with like with wider prongs in them. Yeah. Maybe I'm not thinking about that in the right way.
Good question. So yeah, in general, the kinematics for this are a bit complicated. And I will say that based on these data, I mean, I don't think there's a good argument for like a very strong jet energy dependence given the energy cycle. That being said, right? So momentum is essentially along this direction, right? Whereas when you think about the role of the color coherence, right, that's more related, I think, to kind of the transverse direction, right? Mm-hmm. So this depends on kind of if, not only does it depend on the coherence effects, but also kind of depends on if there's angular modification, which is shown by the RG.
Yeah, exactly.
Well. So I think there's like a non-trivial dependence of both ZG and RG, and it's kind of difficult to only talk about one. Mm-hmm. In vacuum, right? You have to compare both. I will say that this Elise paper is really nice because they actually do measure ZG in the exact same paper, and that's actually very nice because you can actually see how both of them change together.
Yeah.
Or at least change from the same experiment.
Yeah, exactly. Because I mean, yeah, you see the modifications here, and then ZG. So like I think of ZG more as like the splitting function, and then like RG is a more natural probe for like coherence effects.
Sure.
But I'm not sure if that's just biased by the fact that we see a modification in one and not the other.
I will also say that, I mean, I would say in both this paper and in my opinion, this paper, that the conclusions regarding coherence are not, really strong at this point in time. I think there's still a lot of work to be done. For example, trying to reduce systematics to increase our understanding at the theoretical level in order to make better comparisons. Mm-hmm. So I think there's still a lot of interesting work to be done here with regards to that. Yeah.
Okay, thanks.
So thanks for the very nice talk. So you also showed really nicely that you can go back to the left data, and even there's discrepancies. I mean, is it understood what kind of physics is missing in the generators? Or
okay, so I can give you
yeah, it can be brief because I understand very little. So a big picture is good.
Okay, so this is what we did in proton-proton data. And you can just look at the bottom here. So, for example, this is multicolor generators divided by the data. You can see there's this rising trend for this array and this kind of lower trend for idea. It's actually the exact same trend we saw in left with the same generators. So I think this is related to the hybridization model because one of the major differences between Pythia and Herwig is Herwig uses the so-called cluster hybridization, where you kind of put partons together that are kind of grouped together into a hadron, whereas Pythia uses what's known as string fragmentation model, where there's a color string that connects them, and you slice the string at various points to make them. And so these do have kind of different patternization models. And so, I mean, this could be one of the reasons why you see this discrepancy. That being said, it also has like a ZG dependence to it, right? If there's only the hadronization model, perhaps it would only be kind of flat above and flat below. So I think it's some non-trivial dependence of maybe the hadronization model with maybe some of the treatment of the parton shower. Yeah.
Can I ask a follow-up to that?
Sure.
So I was also wondering about that in the LF data. So when you, for those models, are they tuned to only E plus and minus data, or do they also include the?
Good question. So maybe I can go to the. Sorry, my talk has many animations, so sometimes takes a while. Okay, so yeah, so for example, when we're doing this left comparison, so the Pythia 6 here is a little bit different than the other models in the sense that this Pythia 6 was actually given to us with the data. So this is essentially Pythia that has been generated a while ago, right? Now, I don't think it was generated like 1990 or something. It was something they did after the lab shut down, and they did it before the collaboration was all. Okay. The rest we had to generate because Pythia 8 didn't even exist. Right? So we generated these. Pythia 6 was something that's a bit unique, but in that sense, right? I think these 4, they will most likely have had a very large amount of data from left to T2, right? Most like fragmentation, function, all of this stuff are tuned to some extent to that data, right? So there's already a lot of tuning. The Pythia 6, I'm not so sure about actually because it came earlier. But I should also point out this particular observable didn't exist when WEP was created, right? It was only thought about in like 2010. So it was not tuned to this specific observable; it was tuned to some other data.
Right.
Good question. I don't listen. Can I ask one small question? So I think it's slides 51 through like 53. And it's in particular when you're, exactly here. So going forward from this observable onto what has been observed, let's say like these with respect to these multiplicity BP events, where we see the surface enhancement here. Yeah. And then with respect to, I guess you show a plot for this jet observable of soft probes across charged particle multiplicity. So here we see this upward trend that sort of like levels out. Yeah. And then in the plot, you have the opposite in which you have a downward trend, and then there's a leveling out. So I guess you mean here. Yeah, exactly. So I guess like my question was, there's 2 questions. Like A, why are they qualitatively different in this sense? And then B, why is it that it seems as if after you cross charged particle multiplicity density of 20, these observables seem to be flat? Well, what could that potentially say about this probe as maybe a signature for QGP formation?
So I think we should be careful here because I think there's a distinct difference here in the sense that these are minimum bias proton-proton, right? So when you're looking at minimum bias collision, like let's say 5 particles per unit of affinity, that's really like soft physics that you're studying, right? If you look at a jet with let's say 10 particles, that's like a completely normal jet. Most jets at LHC, these energies have like the average is like 20 particles, right? So 10 to 20 is really not that important, right? So like this could be like, this is probably QCD that moves in the shower combined with the hadronization model. Whereas this is like really probing like probably your non-perturbative dynamics of very soft interactions in the minimum bias, right? And so then the question is, so I think basically what I'm saying is that the trend is different, but also we're probing different physics down here, right? And then the question is, if we go to large multiplicities within a jet, if some of the trends of the non-perturbative kind of dynamics here also kind of sneak into the jets somehow, right? So that's kind of what we want to study. So perhaps maybe, you know, like this ratio starts going up like this or something like this in relation to kind of what we see as you have more particles in a small region. So there potentially can be interaction between them of a non-perturbative region.
Okay. Gone a little bit over, so let's just thank Austin for a wonderful talk.